Welcome, students. In this video, we are going to study confidence intervals. Let's start by looking at the following problem. An engineer wants to estimate the mean cold cranking amperage for batteries of a certain design. He draws a simple random sample of 100 batteries and finds that the sample mean amperage is X bar equal to 185.5. And the population standard deviation is given as sigma is equal to 5. Let's assume that we would like to make some inferences about population mean, which is unknown in this case. So probably we would like to start with using X bar as our point estimator. So X bar is equal to 185.5 is our point estimate of population mean, which will not be exactly equal to the population mean. Point estimates, no matter how they are determined, share the same fundamental weakness. They provide no indication of their inherent precision. The population mean will actually be somewhat larger or smaller than 185.5. To get an idea of how much larger or smaller it likely to be, we construct a confidence interval around 185.5 that is likely to cover the population mean. We can then quantify our level of confidence that the population mean is actually covered by the interval. So basically here we have a population for which we do not know population mean. We do know population standard deviation is equal to 5. We do not know what is the PDF for population. We don't know what distribution those x's are going to follow. We draw a sample of 100 elements from our population. N is equal to 100 is our sample size. Then we calculate X bar, and we would like now to build a confidence interval around X bar. So we'll start by using central Limiterium. So from central Limiterium, we know for large N, in this case, we'll assume that N is large, is greater than 30. We know that X bar follows normal distribution with mean the same as population mean, mu, and variance that is equal to sigma squared over N. So in our case, X bar follows normal distribution with unknown mean mu, which we are trying to find, and sigma is equal to 5, so this is 25 over 100. So this value here is also known as mean standard error, or also standard error of the mean. So X bar follows normal distribution with mean mu and variance, which is equal to sigma X bar squared, where sigma X bar is standard error of the mean, given as standard deviation of population divided by root of N. Now then X bar minus mu divided over sigma of X, or sigma divided by root of N, is going to follow standard normal distribution with mean 0 and variance of 1. Here is a PDF of standard normal. Then if we want our standard normal random variable to lie in the following specific interval from minus 1.96 to 1.96, probability of that is equal to 0.95, 95%. So we have an area of 95% in the middle here, and areas in the left and right tails are equal to 0.025 or 2.5% in each tail. All right, now here we can express this as the following probability. Just substituting this instead of our z here, we'll get the following expression. Now, doing some algebra here, let's multiply all sides by sigma over root of n, which is obviously always positive, so it will not change signs of our inequality. And let's subtract let's subtract x bar from all sides here. We'll get minus x bar minus 1.96 sigma divided by root of n. This is then minus x bar plus 1.96 sigma divided over root of n. So probability of that is equal to 0.95. All right, now multiplying all sides of our inequality by -1, we'll get probability that sigma lies in the following interval, x bar minus 1.96, that our mu lies in the following interval, x bar minus 1.96 divided by root of n less or equals than mu, less or equals than x bar plus 1.96 sigma over root of n. So that probability is equal to 0.95. So here we built our confidence interval. Population mean is unknown, and we are giving probability that it lies in the following interval as 95%. So this value here, so our 95% confidence interval is then given as x bar, which is our point estimate, plus minus x bar, plus minus 1.96 sigma over root of n. And this value here is known as margin of error, which is equal to critical value multiplied by standard error of the mean. All right, once again, confidence interval is then calculated as point estimate plus minus margin of error, where margin of error is equal to critical value multiplied by standard error. I will explain in a second what do we mean by critical value. Now let's in fact calculate the values for boundaries of our confidence interval. Then our confidence interval is following 185.5 plus minus critical value of 1.96 multiplied by standard deviation of population 5 divided by root of sample size, which is 100. So this is 10. So here is our 95% confidence interval. Now, what do we mean by our 95% confidence interval? It's tempting to say that our confidence interval will contain true population mean with the probability of 95%. However, this exact phrasing that I have used just now is not entirely correct, since probability refers to random events that have random outcomes. However, in this case, endpoints of our interval are fixed. True population mean, the value of true population mean is also some fixed value. So the value of true population mean exists, it's just that we do not know it. So there is no randomness involved at all here. True population mean will lie in our interval or it will not. So by this reason, we use the following phrasing. We say that we are 95% confident that our confidence interval will cover true population mean. What do we mean by that? If we were to repeat the following experiment of drawing sample sizes of hundreds and measuring X bars and following this procedure of creating confidence intervals, then out of 95% confidence intervals that we have built, then 95% of them are going to cover true population mean, and in other 5%, our confidence intervals that we are going to build using this way will not cover true population mean. All right, now, so basically confidence level is given as 1 minus alpha multiplied by 100%. Confidence level, so I will explain in a second what do we mean by alpha here. By confidence level, we mean the proportion of all possible samples for which the confidence interval will cover the true population mean. All right, now what do we mean by critical value? So here in this example, we built 95% confidence interval, meaning that we can build, generalize and build a confidence interval of any confidence level. So we can build 90% confidence interval, meaning that 90% of all possible intervals that we are going to build using this procedure are going to cover true population mean, or we can build 60% confidence interval or any confidence level of your choice. But the most standard confidence interval is 95% confidence interval. Okay, now what do we mean by critical value? In our case, in our problem here, critical value was equal to 1.96. So this value here is given as z alpha over 2. So we want 95% of area to be lying around our mean here of standard normal, which means that to the left of this point, we have 95% plus 2.5%, that is in the left tail here, area lying to the left of this point. So probability is that our random variable z is less or equal than z critical value z alpha over 2 is equal to 0.975. So this value here is basically the value of CDF, the value of such a point where CDF is equal to 0.975. And this value is equal to 1.96. When alpha is equal to 5, when alpha is equal to 5% or 0.05. Now, if we wanted confidence interval of other lengths, let's assume that if we wanted to have a confidence interval of 68%, a 68% confidence interval such that 68% lies in middle here, then, so let me draw that in a different color, in a blue one. So this corresponds to confidence level of 68%. So this is alpha then is equal to 32. And 32 over 2 is then 16 z minus 0.16. Not 0.16, but 0.16. And positive value here is z subscript 0.16, right? Such that we have 16% of area lying in the tails, in the left and right tails. All right, now this point is equal, this critical value is equal to 1. and negative value given as -1. And so on. If we would like to build confidence interval of any arbitrary level, then we would go to our standard normal table or use statistical software. Then we need to find such a point where CDF of standard normal is equal to, in that case, 0.64, 68% lying in middle, plus 16% in the left tail. So this is 84. So 0.84. Then we would go to our standard normal table or use software to find this critical value. Now let's take a look at the following three cases. In the first case, we have critical level of 68%. So 68% confidence interval. In the middle, we have 95% confidence interval. And in this case, we have 99.7% confidence interval. So critical values in those cases, critical value here for O16 is equal to approximately 1. In this case of 0.25, O25 is equal to approximately 2. And in that last case, Z of 0.03 divided by 2. So this is 1.5 is approximately equal to 3. Then you can see the lengths of our confidence intervals. So let's recall the way we build our confidence interval is X plus minus critical value multiplied by standard error. So standard error is the same for all the three cases. X bar is, so X bars are going to vary from case to case. So basically what we are doing here is we are repeating our experiment of drawing samples of sizes 100 and measuring X bar. And then we are building different confidence intervals of confidence level 68%, 95%, and 99.7% for each X bar. So here we do our experiment one time. So let's call this X1 bar. Then we repeat our experiment. We draw a sample of size 100 again. So this is X2 bar. And then we build different confidence intervals of different confidence levels. Now, if we repeat that experiment like several times that we simulated here, this black line for mu shows the value of true population mean. So basically we are doing simulations here. And we see that in 95% of confidence intervals that we built using the procedure above, so 95% of those intervals are going to cover true population mean. So as you can see, in approximately 95% cases, the true population mean will lie in our interval. So there are some cases where our interval is far to the right of our true population mean or far to the left of our true population mean. So 5% of those intervals we are going to build in that way are going to not cover true population mean. If you pay attention to our formula here, you can see that the width of 68% confidence interval is smaller since the critical value here is smaller, meaning that the width is the margin of error is going to be smaller, meaning that the width of our confidence interval is smaller. So our but decreased width of confidence interval also means a smaller confidence level. So as you can see, there are far many intervals that are not going to cover true population mean if we compare it to 95% confidence interval. However, the width of that confidence interval is smaller. And as we can see in the last case, almost all intervals, I believe, in this simulation, all intervals cover true population mean. But however, we can see that the width of confidence interval is larger. All right, guys, now let's summarize some important points. We started with a case when true population mean was unknown. Population standard deviation was known. We didn't know which distribution, what is the distribution for our population, but it was okay since we used central Limiterium here. We were allowed to use central Limiterium here. Then we calculated X bar, our point estimate, and then we built our confidence interval around our point estimate by calculating margin of error. Okay, guys, now let's move on to the next case. Let's assume that we have similar example. However, in this case, let's assume that true population mean is unknown. So we will try to make some inferences about true population mean. Let's assume that population standard deviation is known. So this is known. Now let's see what happens if, for instance, we draw a small sample. Let's assume that we are drawing a small sample where n is less than 30. Let's assume that n is equal to 4. So let's assume that n is equal to 4. So we have 4 sampling points, x1, x2, x3, and x4. So we again calculate X bar. However, in this case, we are not allowed to use central Limiterium because our n is small, and central Limiterium is an asymptotic theorem for large values of n. However, if sigma is known, then we know that sum of random variables x1 plus x2 plus x3 plus x4 will also follow normal distribution. Normal distribution where n is equal to the sum of means. So the mean of x bar is equal to mu, mean of x1 is equal to 2, mean of x2 is also equal to mu, and mean of x3 is also equal to mu, and so on. So we have mu plus mu plus mu plus mu. So this is 4 mu, and their variance is equal to the sum of their variances is equal to then 4 sigma squared, since variance of each xi here is equal to sigma. Now, if we calculate x bar is equal to x1 plus x2 plus x3 plus x4 divided by n. Now this sum is going to follow normal distribution with mean is equal to then expected value of x bar is equal to 1 over n, expected value of x1 plus x4. Each expected value is equal to mu here. So this is 4 mu divided by n is equal to 4. So this is mu. So x bar is going to follow normal distribution with mean mu, and variance that is equal to, so if you recall, variance of x bar is then equal to 1 over n squared. So variance of the sum So this is 1/16 multiplied by 4 sigma squared. So this is then sigma squared over 4, where variance is equal to sigma squared over, let's generalize our case. Let's replace 4 by n. So we can see that X bar here, when sample size is small, but if sigma is known, then we can simply use the linear combination of normal random variables to show that X bar is going to follow normal distribution with mean mu and sigma and variance of sigma squared over n. So this is the same case as if we were to use central Limiterium. So you can see that here, here our X bar also follows normal distribution with mean mu and variance of sigma squared over n. Meaning that when building confidence intervals, in the case when true population mean is unknown, but standard deviation of population is known, then we can use the same procedures that we used above. All right, now let's consider another case. So in this case, again, we can use standard normal distribution to build our confidence interval. So confidence interval in that case will be X bar plus minus critical value, where z follows standard normal distribution multiplied by standard error. So standard error is given here. So standard error is given as sigma over root of n. All right, now let's consider another case. Let's assume that we would like to make inferences about population mean from a population where mu is unknown and sigma is also unknown. Also, guys, I forgot to mention, let's assume in that case that this time we know that PDF of our population is normal. Otherwise, we would not be able to use this step here, since we said that Xi's they follow normal distribution with mean mu and variance of sigma squared. Okay, otherwise we wouldn't be able to use linear combination of normal random variables. All right, and now. However, in the very first examples that we considered here, it was okay if PDF of population was unknown, because here we are using central Limiterium. In second case, here we should know PDF since we are not using central Limiterium here. Now let's further generalize our problem. Let's assume that population mean is unknown and population standard deviation is also unknown. Let's add assumptions that population follows normal distribution. So PDF here is given as normal. Let's assume that we draw a sample of size n, where n is small. So what we have here now, n is small, meaning that we cannot use central Limiterium to say that X bar follows normal distribution. Also, we cannot use linear combination of normal random variables since sigma is unknown. If you recall from previous case, here we have shown that X bar follows normal distribution with mean mu and a variance of sigma squared over n. So we need sigma squared here if we want to show that X bar follows normal distribution with this variance here. So now we have a problem since sigma is unknown, so we cannot use either central Limiterium or a linear combination of normal random variables. However, it turns out it turns out that if we look at the following random variable, x bar minus mu divided over s over root of n. It turns out that this random variable follows student t distribution. So if you recall, if we would have known sample standard deviation, then x bar minus mu over sigma divided by root of n, that follows standard normal distribution with mean 0 and variance of 1. Now, the only difference between those two random variables here is that we replaced unknown sigma with s here, where s is population standard deviation, which is equal to root of squared deviations from mean divided over n minus 1. Why we are using n minus 1, I will show you guys the reason why we are using n minus 1 instead of n when calculating population standard deviation in another video. The reason for that is such that as S here is an unbiased estimator for sigma. We'll get back to that in more detail in our another video. All right, so it turns out if we replace sigma by S in our random variable here, then this random variable follows new distribution known as student t distribution. So student t distribution is a family of distributions discovered by William Gasset, who was a head brewmaster at Guinness Brewery. He was not allowed to publish under his real name, so he used the pseudonym student. And if we have xi's, where n is small, is a sample from normal population with mean mu, then quantity x bar minus mu over sample standard deviation over root of n. This random variable here follows student t distribution with n minus 1 degrees of freedom. So student t distribution, in fact, is a family of distributions indexed by degrees of freedom, where degrees of freedom is equal to n minus 1. So sample size minus 1. So for each sample size, for each degrees of freedom, you will have a slightly different shape for the PDF. We can see that from the following nice pictures that I have stolen from Wikipedia. Here is a plot of, in red, we have student t distribution. In red, we have student t distribution with degrees of freedom equal to 1. So sample size is equal, n is equal to 2 then. And in all these peaks in blue, we have standard normal distribution. As you can see, student t distribution is a distribution that has similar shape to standard normal, but is a little bit flatter. And when we increase the degrees of freedom, here in green we have n is degrees of freedom is equal to 1. In red we have degrees of freedom is equal to 2. And in blue is our standard normal distribution. And then if we increase degrees of freedom, we can see that student t distribution is going to extend and will try to reach and match a standard normal distribution. And in fact, we can see that when degrees of freedom is equal to 30, those red and blue PDFs, they almost overlap. And we can check that by looking at the percentiles of student t distribution and standard normal distribution. So here is 97.5th percentile for student t-distribution with degrees of freedom equal to 4. Here is the 97.5th percentile for standard normal. And as you can see, when we increase the number of degrees of freedom, the difference between those two values are going to decrease. And when n is equal to 30, they are almost equal to each other. When degrees of freedom is equal to 60, we can see that they get even closer. And obviously, when degrees of freedom is infinity, then student t-distribution will exactly match a standard normal distribution. Now, coming back to our problem, now we know that this random variable follows student t-distribution. Let's draw its PDF here with n-1 degrees of freedom. And then if we want to find probabilities that this random variable lies in interval, let's say from minus t, let's use the following notation. T subscript degrees of freedom, and then alpha over 2 to positive value. So here we have mean of 0, positive value of t, n-1, alpha over 2. The probability that our random variable lies in this interval is then given as alpha, where 100 multiplied by 1 minus alpha % is our confidence level. So then probability that our random variable lies in that interval is given as x bar is given as alpha. And then performing similar operations that we have done here in case when we're working with standard normal distribution, then following basically similar operations, we get the confidence interval. In the case when our sample is small, it comes from normal distribution with mean mu, and sigma is unknown. Then we built our confidence interval around point estimate using now critical values that correspond to percentiles of student t-distribution. Okay, so the only difference between, if we compare that to the way we have built confidence intervals in previous cases, the only difference is that now we use different critical values. We use quantiles from student t-distribution, and we also replace sigma with s since population standard deviation is unknown. All right, guys, this will conclude our lecture on confidence intervals. In the next video, we are going to cover chi-square distribution, and we will build confidence intervals for population variance. All right, guys, thank you for watching.